Hey, good morning, YouTube subscribers, Fidevil subscribers, and anyone else on LinkedIn. I wanted to go over once again this first order RC circuit sourceless and first order RL circuit sourceless because the waveform trace in the previous video was not very clear. So I wanted to redo the simulation. However, I wanted to taken another attempt at explaining the RC circuit and the RL circuit. The capacitor acts as a temporary battery, and it is something that can separate the positive and negative charges on two different plates. However, it also acts like a spring. So when you have a source connected to the RC circuit and you disconnect from the source, a voltage source that is, then you'll see that the capacitor acts as a temporary voltage battery, and it is able to send current back into this resistor until it depletes to zero. And this first order RL circuit, I was explaining yesterday that the inductor has current flowing through it. In DC, it acts as a wire. However, as the current continues to flow through it, the current changes from a current through the wire into a magnetic field. I forgot to mention that in the previous video. Into a magnetic field. So so as the current continually flows through and changes in magnitude through the RL circuit, it also builds a magnetic field, and it builds the magnetic field, and when the magnetic field collapses, it turns back into current and flows through this resistor. So once again, this inductor resists the inertia that occurs when we disconnect it from the voltage source. So if the current is flowing in one direction and you disconnect it from the voltage source, it will continue to want to flow in the same direction until it depletes to zero. And I wanted to point out that if you're working with these waveforms in LT-Spice or any other Spice, you can change the line thickness. This was originally a 1, and then the line is not very thick to be observable under the graph or the plot. So I'm changing it to 5 for the line thickness. I'm going to click OK here, and then we're going to resimulate it. And then you can see here, VA is this first exponential e to the negative t over tau is going to be this RC circuit over here. You can see that the voltage is depleting over time, and it's depleting over time. Actually, let me delete this so that we can see things clearly. The voltage of this capacitor C1 flowing through this voltage and current flowing through this resistor is going to deplete over time over here, and it has an e to the negative t over tau exponential, where tau is the RC constant. Okay, and then I'm going to delete this graph over here, and then we're gonna add in the current of RL, and this one is of the opposite circuit, in which the positive is on this side, the lower side, and negative is on the top side. However, the voltage of this inductor, this current that's flowing through, so notice that the other graph was a voltage, this graph is current. This current is going to deplete over time until it depletes to zero, and it is e to the t over tau time constant in which tau is L divided by R. Remember, the tau of the RC circuit is R times C. The tau of this RL circuit is L divided by R, and I set them equal to each other so that they both deplete at the same time. On another note, I wanted to point out that there's this great simulation software called. Is there a way to I guess maximize the screen? I guess not. This is a great website by Paul Falstad, falstad.com/circuit /circuit/, and it is a Java applet of several circuits, from the basics to some more complex circuits. And since we're working with resistors and capacitors and inductors, this original circuit that appears in the default setup is an RLC circuit, in which there's oscillations. It looks like a sine wave that oscillates over time. However, we're going to go look at some examples, such as the capacitor over here. You see there's a positive voltage source, or a DC voltage source, in which it charges the capacitor and resistor pair over here. This is a series RC circuit, rather than the one that we see where it's a parallel. So this one, it charges the capacitor over time, and then when you disconnect it to the secondary circuit over here, when you disconnect it, you'll see that it acts like a spring. The spring has been compressed, and then when you disconnect it, you'll see that the electrons are flowing in the opposite direction. Once again, the electrons are flowing in the clockwise direction on this side of the circuit, and then when you disconnect it and connect it to the secondary circuit, it charges. It has been charged, and it discharges, and it flows through the resistor, and it flows to the electrons flow to ground. Likewise, we're going to look at the inductor circuit now. Similar to the one before, but this one has an L, or it has an inductor. Remember that the explanation for the inductor is that the change in current turns into a magnetic field. It turns into a magnetic field until it collapses. It charges into, instead of separating the charges into capacitor plates, it turns into a magnetic field. And then when you disconnect it into the secondary circuit, the flow of electrons continues to flow in the same direction. Once again, it flows clockwise here, and then here it flows counterclockwise. So I hope that makes sense. I encourage you to check out this Falstad.com by Paul Falstad. Very generous, computer scientist and engineer that wrote this free applet. If you would like to contribute to this project, or donate to his work, then please do give him some recognition. Thank him for his work. Send him an email. So that was the Falstad.com circuit. You can download a local version of the app to your MacBook or your Windows PC or your Linux PC. Once again, this was what we were working on today. Wanted to show this one more time. The thickness of the curves over here have been changed so that you can more clearly see. And I'm going to right click here, and then we're also going to add a grid to see that it lines up nicely with the grid as well. Okay, well, thank you for tuning in, and I hope you have gained something from this video.